Okay, so last time Saket started path covers, right? And he stated a nice theorem for path covers. We'll prove that theorem today, okay? So, it was given by Galai and Milgram. Am I not wrong? Okay. So the theorem is that for every graph G, there is a path cover. Is it visible? I think it is. I should try. Path cover P and okay. So the theorem says that for every graph G, there is a path cover P and an independent set which contains elements Vp, and for every path P in pcal, this Vp vertex belongs to P. So basically, if we have a path cover, so for in path cover, there exists an independent set such that each vertex belongs to one path. So from each path, we have one vertex in the independent set. Okay. And path cover, you remember? So set of paths, disjoint paths which cover the entire vertex set. Okay, that is called a path cover. Union of paths. So a path cover is basically a union of paths such that disjoint paths, they are disjoint. So vertex disjoint paths in G such that union of Pi is, it covers the whole vertex set. So this is a path cover. Okay, so we'll prove this. So we'll prove this by induction. Okay, so we'll prove this theorem by induction, and to use induction, we'll prove this theorem for a minimal, not minimal path cover exactly, but a path cover which has minimal set. Okay. So basically, path cover is minimal. So we will take, we'll prove the theorem for a minimal path cover, but I'll define what is that. Okay. So
what is small p there?
this is path in this path cover. So path cover is a set of paths, right? So
G subscript p
is some
vertex belonging to that.
belong to that path P. Okay. Okay. So instead of proving this, we'll prove the theorem. Okay. We'll prove that. Okay. Let's first define vector of P. Okay. Okay. So let's P is a path cover which has paths P1, P2, Pm. Then ter P contains the elements, the last elements of these paths. Okay. So, for any path, and we are in directed graph, sorry, every directed graph, we are working in directed graphs. Okay. So, for every path we have path like this. So, this last vertex, this is called terminal, right. So, basically this ter P is the set of all terminals, all terminal vertices of this path. Okay. So, V1, let this ter P is V1, V2, Vm. That means that P1 ends at V1, P2 ends at V2. These are the terminal vertices for these paths. Okay. So, we will prove this statement that for path cover P with terminal P, for every path cover P such that this set ter P is minimal we prove for every path cover P such that this terminal set is minimal, we prove that there is an independent set Vp such that P belongs to path cover. Okay.
What is meant by terminal is minimal? So, how many paths is there, that many vertices will be there?
Yeah, exactly, that many vertices are there, but minimal means that we cannot have a path cover with exactly a subset of this ter P. So, basically if we have this path cover P1, P2, Pm and its terminal set is this. So, I will say that ter P is minimal if there is no subset of ter P such that we have paths, we have a path cover corresponding to this. Okay. So, basically
That means path cover is minimal, same thing, right?
this is I think one way is true, but the other way, this is like more stronger condition. It is not only minimal, but we are talking about the end points of it. So, for a path cover you may say that maybe these kind of thing we can take, but it will also be containing these. So, but if you think that it is more stronger condition, because we are talking about particularly the last vertices, that we do not have any path cover which has strongly like a proper subset of this as a ter P, as the terminal set corresponding to that path cover. But yeah, that is true what you are saying, that it is like minimal kind of, but yeah, we are not defining that with it, it is minimal. Okay. This is corresponding to this terminal set. Okay, so we will prove this statement. Is this okay? So, this is enough to prove, right? So, for every path cover P such that ter P is minimal, there is an independent set Vp such that P belongs to, for every like P path in path cover. Okay. So, we will take this. So, let we have.
Okay, I have one question. So, there is an independent set Vp. Does that mean that from each path we are taking one vertex in the independent set?
Yes, I think I have written it. Vp belongs to P for every P in path cover. It is yes. Okay. it means this. Okay, so we have path cover P, P1, P2, Pm, and its terminal set is V1, V2, Vm, and this is minimal. Okay, is minimal. So we assume that it is minimal, and now we will use induction to prove this statement. Induction on n. Okay. Yes. Okay, so how these paths are? This is P1, P2, this is my Pm, okay. And P has the last vertices of the paths. So basically this is V1, this is V2, and this is Vm. Let's write it here. Okay. So what is base case? What will be the base case here? N is equal to 1. So for 1, this holds, right? We have trivial path on one vertex and independent set as well. Okay. So base case we are done because we have this. This is path cover and this is also the independent set. Okay. So now so this is base case. Now we are here in this case. So what can we say about this terminal set? What is our goal? We want to find some independent set such that we have one vertex corresponding to each path. Okay, that is our goal. So what if so first we should check with the terminal set itself whether it is independent or not, because if it is independent then we are done, right? We already have the independent. So if P set is independent, then we are done. Okay, so this is not independent. So assume that P is not independent. That means there is some edge. There is some edge here among the terminals of these paths, right? So without loss of generality, let's assume we have edges between P2 and P1. So we have edge, this edge, V2 to Vn. So let V2 V1 is an edge. Okay, this is not independent, this is an edge. Now what we want to do? We want to prove this by induction. So somehow we want to reduce the size of the graph so that we can use induction hypothesis. Okay. So what we will do here? We can so you see that P2, V2, V1 is a path, is another path. P2, V2, V1 is another path, and okay. So now P2, V2, V1 is a path, P3, Pm, and for first one, because I am instead of P2 I am taking V2 to V1 also. I am extending this path P2. So what will be my P1? P1 minus V1. So basically it ends at some vertex V which is like adjacent to V1. Okay, so say V is the neighbor of V1 in P1. So my first path will be P1 ending at V. Okay, P1 ending at V. So this is my path. So this is my another path cover, right? But can we make sure that this vertex exists?
Yes, it is a path, but it will be there.
But we have trivial paths as well.
It's not there, then number of paths will be less.
Yes, exactly. Then if V is not there and if V1 is the only vertex in P1, then it is not a path cover with minimal terminal set, because we can take this path P2, V2, V1 and this this new path cover has a proper subset of terminal set here. V1 is not, V2 is not there basically. So that's why V exists, okay, because of so why I'm writing it this. So due to choice of terpy, like minimality of, or we should due to minimality of terminal set P, V exists. Okay. Okay, this is okay. If I remove V1 from my graph, then give me a path cover in G minus V. What is the path cover? P1V, P2 as it is, and Pm. So this is a path cover in G minus V1. Okay. So now, and notice that this, in this path cover, if I am able to find such an independent set, then that independent set would work for this path cover as well, right, in G. Is it okay? So if for G minus V1 on this path cover, if I get some independent set, then that independent set will work for this path cover as well, right? Same. Okay, so that means this is enough, that if we just want to know that whether there exists some path cover, some independent set for this path cover or not. Okay. But to apply induction hypothesis, one more thing we require. What is that? So we have this path cover. For this path, and this path cover is G minus V1. We know that by induction hypothesis in G minus V1, this holds, right? This theorem holds. So we can use that, right? But can I apply my hypothesis now in this stage?
Do you not have to show that this is minimal?
Yes, exactly. So the thing is that if this is P prime, then ter of P prime is, now my terminal set is V, V2, Vm. So the only thing I have to show is that ter P prime is minimal. Because if it is minimal, then this is, and this is a path cover in G minus V1, I can, by induction hypothesis, I can say that there exists an independent set corresponding to this path cover, okay, and that will be my independent set corresponding to path cover in G as well. So this we want to show now, okay, that's the goal. Okay, so P prime is minimal. What will happen if it is not minimal? Okay, let's see. So let terminal set of P prime is not minimal. What does it mean? That there exists a path cover P double prime such that terminal set of P double prime is proper subset of okay. Yeah. Okay, now we have this path cover. So now we don't know like what are the paths, but we know that the terminal set is a proper subset of this set. Okay. So and what we want to do, we want to like okay, there exists a path cover and we want to get to some contradiction, but from where? Note that we don't have V1 here, but in G we have V1. So maybe we can look for V and V2, and in order to get contradiction, we can come up here P and say that like ter P is not minimal. Like we can use this path cover, because we know that we started with some path cover with minimal terminal set for G. So that's why I want to look at V1 as well when I am looking at the path cover in G minus V1. Okay. So that's why I look for vertex V. Okay. So now I have a path cover with a terminal set which is proper subset of this set. So let's see in that if in that set terminal P double prime, this vertex V exists or not. Okay, V belongs to or not. So let if V belongs to, what happens if this vertex V belongs to terminal set of P double prime.
And we have a smaller, we have a smaller path cover for the original.
Yes, exactly. That's why I am just looking at V and V2, because I want to look at V1 as well. So because V is in the terminal set of P double prime, so that means there exists, okay, so this is my case 1 when V belongs to terminal P double prime. It means that there exists some path P in P double prime such that P end set V. Okay, this path ends at vertex P. So now this path P ends at V. All these paths are like this, right? Remember? So these paths are like this. So now if P ends at V, then P V V1, this is also a path, right? P V V1 is a path. So this is a path in G. Okay, this implies P V V1 is a path in G. So what I'll do in P double prime, this cal P double prime, what I'll push this path instead of P. I'll just putting this path. Okay, so my new path cover will be, say, what to say, not or triple prime is P double prime P union P V V1. Okay, I am including this path. So now notice that this path cover was a path cover for G minus V1, right? So this is a path cover for G, right? So this is a path cover for G. But what can you say about the terminal set of it, this path cover? That is subset of P, because this was proper subset of terminal of P prime, but now in P triple prime V1 is also there, so we can compare it with this. Is it okay? But this is a contradiction, because we said that for this P is minimal. This is a path cover with minimal terminal set. So in this case we got the contradiction. So that means for other case we will say that okay, let's V does not belong to terminal set of P double prime. Okay, let V is not there. What else we can look for here? From its path cover we want to go to the path cover, we want to construct a path cover of G. So how can we do that? What other vertex I should look for? V2, because I know that V2 V1 is an edge in G. So let's see where is V2, if V2 belongs to this terminal set or not. So let's V2 belongs to terminal set of P double prime. Okay, and okay, so that means there exists some path P in P double prime such that P end set V2. Okay, so again what can we say? We say that this P was ending at V2, but V2 V1 is an edge in G. So P V2 V1 is a path in G, and so what path cover we will have? P triple prime is P double prime set minus P union P V2 V1. So this is a new path cover. Is a path cover in G. Okay, so now this is a path cover in G. Again we got some path cover. Now what about its terminal set? Yeah, V2 is there. Oh, V2 is also not there now because we have removed P. So V2 is not there. Yes. So V2 is not there and V is also not there. Right? So two vertices are not there. So even if you include V1, okay, V was not there in this P also, right? But now V2 is not there. So basically this is terminal set of P triple prime is a proper subset of terminal of P. This is again contradiction. Is it okay, this case? Confusing?
The previous case, I didn't understand why turn of P triple prime is a proper subset of turn of.
Here? Okay. So
Like, we assume P double prime is some path cover. It could have totally disjoint.
but this was a
The terminal set of P double prime is just P double
Yes, because this is a proper subset of ter p prime, and for p prime and p, what is the difference here in the terminal set of these two? Only difference is at one vertex. Here we have v1, here we have v, right? So only this difference we have. Now when we are saying, so we removed v here when we removed this path p and like extended the path p which were ending at v, we have extended that path and included in the path cover, and that is my p triple prime, right? So instead of v now I have v1, and the other set, like the remaining set terminal p double prime, is a proper subset of what? It is still proper subset of ter of p prime. So it is proper subset of this, and v is not there. That means something is missing, right? Something is missing from this set, and that is why this will be a proper subset of this. Okay. And in second case, it is like even more easy to see, because when we are extending the path which were ending at p, so we are just excluding v2 from the terminal set of p triple prime, right? And so clearly you can see that which vertex is missing in ter p prime. So we get a smaller set. Okay. So this case also is fine. So what else we have now? So one final case. So v is not there, but suppose v2 is also not there. If v2 is there, we will go in this step and we will get contradiction. And so let, if v and v2 both are not there in the ter p double prime. Okay. In this case, what you can say about the set terminal of p prime? And so what is the difference between these two sets? Okay, let's say cardinality. What is the relation between their cardinality? In this p double prime, v, this is not v1, this is v comma v2, both are not there. So what can you say about that? Its cardinal? Strictly less than to वैसे भी था, because we were taking proper, na? So strictly less than was there. But for
Like you are saying only these two are not there. No.
Only we don't know, but at least these two are not there.
So it will be.
This is my terminal p prime. V and v2 is not there.
Two are not there.
At least two are not there, right? So this is at most this minus 2, right? Because v and v2 are not there in p double prime. So at least cardinality 2 difference will be there in between those two sets. Okay. Okay. And this is a path cover for g minus v1. So only v1 is uncovered. Can you give me a path cover for g? Do you have any doubt what we are doing? So we are in case 3. In every case what we are doing, we are just trying to extend our path cover here for this g minus v1 to a path cover of g. Okay, that we are trying to do that. and we are looking at the terminal set of new path cover for G, and from this point we get the contradiction. Okay. So, in these two cases what happened, we said okay, for this path cover P double prime, let us see whether V belongs here or not. If V belongs to this path cover terminal set of P double prime, that means there is some path which ends at V, and so from this path cover I am trying to get a path cover for my G. That I can do because I know that V1 is an edge in G. So, I will just extend that path which was ending at V, I will extend it to V1, and this is my new path cover which has exactly same cardinality of paths, and its terminal set is same, except instead of V now we have V1, right, and that is where we get the contradiction that this terminal set is a proper subset of Terp, because Terp contains V1 and everything else. Is it not okay? In second case we say that okay, if V is not there, then what happens? So, if V is not there, then we will look for V2, because we know that V2 V1 is an edge. So, we can again extend the path cover. So, that is why I am looking at V2, whether V2 belongs to my terminal set of this new path cover or not. So, if V2 is there, then that means there exists some path which ends at V2. Okay. Now, V2 V1 is an edge in my G. So, I can extend this path from V2 to V1, and this gives me a new path cover for my original graph G. And now, if you look at the terminal set of this new path cover, that does not contain V2, because the path which were ending at V2 we extended it to V1. So, V2 is not there in terminal set of this new path cover. So, this is strictly proper subset of this terminal set, and so again we got contradiction, because we started with a path cover with minimal terminal set. Okay. Now, we are in the third case when we are saying okay, now we are saying that V2 is also not there. What happens if V2 is also not there? So, now both are not there, but that means because my terminal P double prime is a proper subset of terminal of this set, terminal P prime, which is this set, and V1 is V and V2 both are not there. That means the difference between these cardinality of this terminal of P prime and terminal of this P double prime is at least 2. Okay. So, that is all what I am saying. And now, because P double prime is a path cover, can you give me a path cover for G? V1, only V1, yes. So, he is saying that let us take P triple prime and take the old path cover, and because V1 is missing, this is a path cover for G minus V1. So, only V1 is missing. So, let us add this new path on single vertex V1. Now, this is a path cover, for G. This is a path cover of G, and now what is the cardinality of this P triple prime? This is terminal P prime, terminal of P double prime plus 1 we have added, but the difference between terminal P prime and terminal prime was 2. So, even if I add one new vertex to my set, it is still less than the set here. Okay, do not look at the cardinality. See, this Terp contains everything. Now, V2 is not there in my terminal set, and I am adding V1, but not V2. So, at least V2 is not there in terminal set of P triple prime. So, if this is my triple prime, so I am saying it is easy to see that V2 does not belong to P triple prime, sorry, terminal set of triple prime. Is it okay? Right? So because it is not in this set, that means this is proper subset of ter P, okay, and which is again contradiction. And we are done because we have covered all the paths. Any doubts? Do you want me to repeat? It's okay. Okay. Or maybe I can repeat, I have time. Okay, so what we did, we wanted to prove that.
Statement. I have doubt in the statements.
What?
Is it saying that for every directed graph?
There is a path cover. There is a path cover and independent set such that this happens. Or you can say,
So
there exists some path cover such that.
Independent set from that path cover.
Yeah, there exists some independent set such that every from each path we have one element in this. These are the same things. Okay. So we want to prove that there exists some path cover P cal and independent set VP such that for every path in P cal we have some vertex in the independent set. So basically you can say that there exists some path cover such that we have an independent set where corresponding to each path in path cover we have one vertex in the independent set. We have such independent set. Okay. So this is the statement we wanted to prove. We said okay, we'll prove this by induction, but we'll prove this theorem that that for any we'll prove this statement for a path cover with minimal terminal set. And what is terminal set? Terminal set is the set of end points of the paths. So if this is my path cover, so my terminal set for this path cover will be the end points of these paths. So P1 at P1 end set V1, P2 end set V2, like that. Okay, and now I want to prove that for every path cover P cal, terminal set of P cal is minimal. Then there is an independent set such that from each path in this path cover I have some vertex. Okay. So we prove this by induction on the cardinality of Vg. And so okay, let assume that we have this path cover P1 which contains m paths and its terminal set is V1, V2, Vm. Okay. And now we want to reduce the, because this is a path cover in G, so this is a path cover in G. So in order to use this like in induction, I want to reduce the size of my graph. So what I'll do, before induction, my goal is to find an independent set such that corresponding to each path I have one vertex in the independent set. So if my terminal set is independent itself, then we are done. This is the required set. Okay. So suppose if it is not like it is not independent. If it is not independent, that means there exists some edge among these. So without loss of generality, we can assume that okay, we have an edge between V2 to V1. So V2 V1 is an edge in G. Okay, and now V2 V1 is an edge, and in order to use like induction, I want to reduce the size of the graph. So I'll remove V1 and now look at the G minus V1. So now for G minus V1, again I'll get some path cover. So from this I'll get a path cover for G minus V1, and what will be that path cover? P1 was ending at V1. So, if I am removing V1 from the graph, then let us remove V1 from this path. So, if V1 was like adjacent to this vertex V in P1, so now my new path cover is P1, which is ending at V, P2 and Pm. So, this is my path cover for G minus V1. Okay. Now, and its terminal set is, earlier it was this, now instead of V1 my first path is ending at V. So, this is my new terminal set for path cover P prime. Now, because we are proving this statement and which holds for minimal terminal set. So, in order to apply my induction hypothesis, this is a smaller graph, but still I cannot apply my induction hypothesis because this condition I have to check. Okay. So, we need to check that terminal of this P prime is minimal. So, that is our goal. Once it is done, then we can apply induction hypothesis and we get some. Any doubt, Ankit? Are you saying something?
No, nothing.
Okay. Yeah. So, once we are with minimal terminal set P prime, so we can apply our induction hypothesis and we will get an independent set where from every path in P prime I have some vertex in the independent set, and that the same independent set is independent set for my G as well, right, because of this path cover. In this path cover V1 is not there. So, if I get any independent in P prime, that is still independent in this path cover as well. Okay. So, the only thing we have to show is that this terminal P prime is minimal. Now, suppose it is not minimal. If it is not minimal, that means there exists some other path cover whose terminal set is strictly is a proper subset of this terminal set. Okay. So, that we assumed here. Now we look at the vertex V, that whether this vertex V belongs to this new terminal set or not. If it belongs to new terminal set, if V belongs to new terminal set, then I can extend this path cover to a path cover for my graph G, because this path cover is for G minus V1. We were working in G minus V1. So, because V is there, so that means there is some path which ends at V. So, and V1 is an edge in G. So, I will extend that path to PV1 and add it to my this path cover P double prime, and so like this I will get this new path cover for G, which has a strictly smaller terminal set. Okay. Which has strictly smaller terminal set. In second case, if V is not there in the terminal set, then I will look for V2. What happens to V2? Because we know that V2 V1 is an edge, so I still have a way to extend my path cover to G. That is why I am looking at V2. So, for V2, if V2 is there in terminal set, again I will say that okay, there exists some path which ends at V2. So, I will extend this path from PV to V1 and add it to my path cover, replace it to in my path cover, and that gives me a path cover for G. Okay. And again which has strictly smaller terminal set than terminal of P. Okay. And now in the last case we will say that okay, now V suppose V2 is also not there, then what happens? So, if V and V2 both are not there, that means this P double prime, which is a new path cover, its cardinality is strictly like its difference is 2. So, at least 2 vertices are missing in this set terminal P double prime. Okay. That means this P double prime is a path cover which has cardinality which has at least 2 less what you call like paths, and still I need to cover V1. So, again from this path cover P double prime, I will get a path cover in G, and by what I will just add, because V1 is uncovered in G. So, I will just add V1 as a path singleton, and this new path cover is again like strictly this terminal set of this new path cover is strictly contained in terminal of P, again because of their differences too, or you can see that V2 is not there in new terminal set also. So, that is why in this case also we got contradiction. So, we are done. Okay, I will remove this. Okay.
Now we have to translate from this thing we proved to that theorem, right?
We proved, if we have proved for minimal set, minimal such set, then we have proved for graph, because we were not saying that for every path cover, we were saying there is a path cover. So, we have shown the existence, right. Okay, so last time we were talking about Dilworth's theorem also. So, we will see that how we can prove Dilworth's theorem from here, like this is a corollary of this result. So, this follows Dilworth's theorem. So, we will see that how. Okay. It is 90. Okay, so let us see that. So, what Dilworth theorem says? It says that in every finite partial ordered set, okay, this is the statement, but first look at the chain. Okay, so given a partial ordered set, let us define first chain. So, what is a chain? If we will say that a subset of this set P is a chain if for every elements say x1 x2 in T, or not denoted by that. Okay. For we will say that T subset of P is a chain if every pair of elements is comparable So, a subset of this set, partial order set, is called a chain if every pair, this is like pairwise comparable. So, for every pair we can compare these elements. So, if compare means that we can tell whether x1, what is the order, like x1 related to x2 or x2 related to x1, we can tell that. So, pairwise for every vertex, for every pair, we can compare the elements, that is called chain. And anti-chain is if T subset of P is anti-chain if all elements are pairwise incomparable. That means we cannot compare any two elements in this set. Okay, this is anti-chain. So, what Dilworth's theorem says? It says that for every finite partial order set, the minimum number of chains is equal to the maximum cardinality of an anti-chain. Okay.
What do you mean by chain?
Minimum number of such sets, like disjoint sets. Minimum number of chains, like yes, actually this covers the whole set. So, this minimum number of chains that covers नहीं बोल सकते, but its union is P basically. It's with union P. Okay. Yeah, that is important, that this is with union P. So, the minimum number of chains which whose union is P is equal to the maximum cardinality of an anti-chain. Okay. So, we will use this theorem to prove this. Okay. So, to use this theorem, we have to make graphical model for this. So, we have this given this partial order set with the relation. So, what we will do, we will make a graph. So, let us construct a graph G. Okay, graph. So, where for every element in P, I will take one vertex. So, for every EI in P, take VI in Vg, and if two elements are comparable, then we will add an edge. Not only comparable, but say if E1 is related to E2, then we will edge, then add V1, V2 as an edge. So, we are making directed graph. Okay. So, now this is my graph G. It is something like this. Now, let us see how this chain looks like in the graph. So, what is chain? This is a subset of P such that every they are like all the elements are pairwise comparable. Every two elements we can compare. Okay. So, in G, how we will identify a chain in this graph G? by path. Okay. So from a path we can see, because every any two like vertices are adjacent only if they are comparable, right? So if I look at some path here, then that will be corresponding to a chain. Okay. And what is anti-chain here in G? Independent set. Independent because no in independent set no two vertices are adjacent, and here no two elements are comparable. So they don't have any edge in G. So they'll form an independent set in G. Okay. So basically chain is corresponding to a path in G, and anti-chain is corresponding to an independent set in G. So that means what we are trying to prove here in terms of G, like in G, what we are looking for. We are saying here that for every finite partial order set, the minimum number of chains with union P is equal to the maximum cardinality of an anti-chain. So that means what we are trying to prove in G is minimum path cover, because which with union P, that means it covers the entire vertex set, and we are looking for paths. Instead of chains, we are looking for paths. So that means we are looking for a path cover. So we are saying that minimum cardinality of a path cover is same as maximum cardinality of independent set of some independent set.
Okay, I have a doubt.
Hmm?
So, the definition of chain is every pair of element is comparable, right?
Hmm.
So, suppose A, B, C.
Hmm.
So, AB is comparable, BC is comparable, so A and C are comparable, right? But if I take a path, then we are saying if they are comparable, then add a edge. So, what about like which don't have a edge? That two vertices are not comparable, right? I have a doubt there.
If two vertices are not adjacent, then they are not comparable. But we build this graph from here, like partial order set, right? So if we said that E1 E2 is an edge, E1 is E1 comparable to E2 and E2 comparable to E3. So that means in my G I added edge E1 to E2, E2 to E3.
So now my doubt is E1 and E3 are comparable or not?
They are comparable by partial order set, right?
But there is no edge between E1 and E3.
We don't know. There will be an edge by construction, but I am taking a path cover.
No, that's okay. But my doubt is there. So, so is there edge between E1 and E3 also? That is thing.
Yes, there should be, because these two are also comparable.
Okay.
So there will be an edge. But the goal is still to cover the entire vertex set by paths. There we were looking for chains. Okay. So now can we use this?
So any path
Because-
cover size is at least a number of antigens. The maximum number of antigens, because independent set cannot be in the one single.
Maximum number, no, cardinality of huh? Yes.
Cardinality of maximum.
Maximum cardinality of independent set. So basically cardinality of maximum independent set.
It has to be at least that much.
Yes.
And that theorem is at most that much.
Yes. So by this theorem we can say, right? So only construction was there, otherwise it is a corollary actually. So only construction we had to do. Okay. That's all. this chapter is complete now. So let's see. Any doubts or anything? Otherwise, we are done for